Okay, let us start our seminar, and our today's speaker is Pavel Shvechikov, who was recently hired to the AI Center Samsung, so he's our colleague now, and he'll give a talk about variational sequential Monte Carlo methods. Although I expected that he would give a talk about overview of reinforcement learning methods, but okay, hopefully this topic is at least as interesting as reinforcement learning. So.
No. it isn't so interesting as reinforcement learning. However, it's close. It's close to one of its areas, in particular to partially observable market decision processes. So today I will tell you only some basic stuff. So don't be surprised. We will start with introduction of what is state-space models, what this concept is, and how one can make inference under this framework. I will remind you what is importance sampling, and finally we will arrive to sequential Monte Carlo. I will show some definitions and some theoretical properties of it, but I will not show any proofs. And finally, we will arrive to at the end, maybe we will arrive to the topic of today's topic. So, what is state-space models? The graphical model of state-space models is shown on the slide. And in fact, it's a very basic Fitts form. It could be much more complex, much more complex. But for our purposes, this is enough. So, in fact, the state-space models is the collection of two sets of two processes. One is hidden. We will denote it by Z with subscript T, which signifies the time, which goes only forward, and the collection of observed random variables, which is also called the Markov observation process. That is a capital X with subscript also T. So in the very beginning, at time step 1, we have some prior on the latent variable. We will call it mu, and the dynamics of this state-space model unroll into time according to the f. This is a function which we will be talking about as system dynamics. And each time step, this hidden or latent variable z also parameterize the observation function g, which gives us the observation x with subscript t.
Why do you have the same parameter theta for both f and g?
Oh, it's
because we use the same part of network for.
We can untie them or use one capital theta, which will be its own for each of these processes.
So I would assume that theta consists of theta 1 and theta 2, and these are different subsets of parameters.
Yes.
And by the way, I would like to draw the attention of the audience that this is an example of probabilistic graphical model, and what Pasha is going to tell about is closely related to the problems which Anton has just discussed, right, during the reading group. And this is also interesting because we no longer have the course on probabilistic graphical models. So some concepts which Pasha will describe, probably you will not read it anywhere, or at least you will not listen it anywhere. So please be careful.
Okay. So some examples of state-space models include hidden Markov model. This is a kind of model in which the hidden process is discrete, so each Z may be only one of some discrete set. Or the very popular linear-Gaussian state-space model, which is nothing but the system dynamics in that example unrolls according to the linear equation, and with maybe some addition of Gaussian noise. This is true for both dynamics of Z and emissions of our observations.
Is there a mistake when xt equals to maybe ct multiplied by ct?
When xt is equal to what?
The same as
BT and BT in the first formula and the second formula.
Oh yeah, this is a mistake. Thank you. So AT, BT, CT, and DT are just some matrices, and they can be different for different time steps. And the second, the third example is a nonlinear and non-Gaussian model, the so-called stochastic polarity model, which sometimes is used in finance, but I'm not very much familiar with it. But
It's like the guy from Spain.
not very long anymore. Okay, so what is the main difficulty here? The main difficulty is non-linearity. Here we have non-linearity only in observation, process. But we can also have some nonlinear transition functions. So we can transition to the next hidden state, the t, non-linearly with respect to the t minus 1.
So this is non-linear function.
Yeah, and this may be, the f may be non-linear function, and this harms the inference process. And we will see this.
And I guess that exponent is just an example.
Yeah, and the exponent is just an example.
So beta is a number.
Yeah, yes.
And that also.
And that also. Yes.
and sigma is a function.
Sorry?
Is sigma is a
Because
function?
it's
Is sigma?
No, I guess not. This is just a constant. Also. So the goals which are often considered with respect to statespace models are numerous. I just included some of the most popular ones. So the first is the setting when theta is known. So the theta, I remind you, is parameters of our dynamics of the transition function F and the emission function G. And in this case, what we may be interested in is the inference of the hidden states, hidden latent variables Z from the observations from X. And this setting can also be divided in two, maybe also the most popular ones, in the filtering and the smoothing. The filtering is concerned with computing the so-called filtering distribution, that is the distribution on the current hidden state Zt, conditioned on all observation up to the now, when now is a lowercase t. The smoothing is also a popular problem, but is not very popular in reinforcement learning, in robotics, in control, because smoothing assumes you have all your observations, or at least you have some subsequent observations. This capital T is bigger than the lowercase t. It means that you have played or observed the whole sequence. And now you are interested in what was the latent variable at particular time step t lowercase. And the second major setting is when theta is unknown. And this is by a large margin more difficult task, because you don't know what is the hidden dynamics. You need to somehow reveal what this process maybe look like, and you also need to identify this theta. So let me just go into some formulas. So the main, probably the main formula for interest is this one. What do you think? How this formula may be called?
Definition of conditional density.
Okay. Okay, and this is a very interesting one, and we will work with this one for the whole today's talk. So we can split this in the numerator and denominator, and for the numerator we can write the joint probability of all observed and unobserved variables, and we can basically compute it very simple. We can just state what was the prior of that one. When we know what is f in the first setting when theta is null, and we know what is the probability of emission xt conditioned on the hidden state that t. Again, the denominator is probably the most difficult part of this inference process, because you need to integrate out the very high-dimensional vector z. And this high-dimensional vector z may be high-dimensional at every time step. It may be of high-dimensional, say, I don't know, say 1,000, and this only for one time step, and you have, say, 1,000 of time steps. And this is a very, very difficult problem. However, for some simple models, like discrete models, that is hidden Markov models, when the z is discrete, you can do many interesting things. So what you can do? You can do what is written on the slide. What is written on the slide? So we have the same Bayesian formula, and we decompose it. We decompose it recursively. What do I mean by this? I mean you have to identify the posterior distribution on your latent states from 1 to t. You may want to pre-compute the posterior distribution from 1 to t minus 1, and also multiply it by some additional multiplier. And this can be done efficiently in a forward recursion. And what is this forward recursion look like? So let me first focus on the denominator. This denominator will play a crucial role in our talk up until the very last slide. So please pay attention. So we assume that we already computed this is called a filtering distribution. The distribution over hidden state at time t minus 1, conditioned upon all the observed states from the beginning until the t minus 1. So just simple integration of this expression over z t minus 1 and t will give you the denominator, and this integration could be done analytically when the dynamic is when z is discrete, that is in hidden Markov model.
Wait a minute.
Yes.
I would say that you need to integrate only with respect to z t minus 1.
No.
The t.
The t also, because
these are just two variables, right?
Yeah. Yes, this is just two variables. And what was I talking about? So this denominator usually poses significant difficulty if your hidden process, the process which deals with your z, doesn't admit some simple structure. By simple structure, I mean it does not discrete. It isn't discrete, and also it is not Gaussian, because in case this distribution is Gaussian, this distribution is Gaussian, and also this one is Gaussian, or linear-Gaussian with some linear matrices in front of because zt minus 1. You can analytically integrate it, but in case you can integrate it, you can compute the denominator in the first formula, and you can also compute our marginal distribution on observed variables. Yes.
I'm sorry. From where do we obtain the last term p of zt minus 1 given x from 1 to t minus 1?
Yeah, this is basically the recursion process. You can always, what you can do, you can always start from the very beginning, from the first moment. Then in the first moment you can compute.
By the way, you can use it. Yeah.
Yeah.
I understand that at every moment t we have p z of from 1 to t given x from 1 to t. But in order to obtain z t given x from 1 to t, we should
if you have
integrate under z out.
Yeah, if you have this one,
Yeah.
you can integrate all the prefix up until t minus 1.
Okay, it is tractable. We can do it.
We can do it in some cases, and we will see what we can do if we cannot do it directly in a few moments. So we cannot do this integration, and we cannot compute the marginal distribution on our observed data if the dynamics is non-Gaussian, non-linear, and all and everything is highly dimensional. This is a difficult problem, and this problem really puzzled many researchers for really, I'm not joking, for about 30 years. They have explored different approximations, and they did so very intelligently. But in mid-90s, in mid-90s, an interesting concept emerged, which is called Sequential Monte Carlo, and which is the topic of. We will see and talk about it in a moment, but before, let us try to do a Monte Carlo integration. So the basic task we want to do is to do Monte Carlo integration. We want to know how to integrate out this latent process, and we integrate it out because we don't know what exactly these latent variables were. They are latent, they are hidden. So the one simple strategy was to use just Monte Carlo integration. But some wise men say to us that the only good Monte Carlos are dead Monte Carlos. We don't believe them. We don't believe them, and we try to do so anyway. So for now, I will step back from the filtering context, from the notation P of x and z, and I turn into notation of some P, Greek P, and of sampling from a normalized distribution in general. This is because I want to introduce a sequential Monte Carlo as a general framework, not as a particular application for filtering. So, so for now, what we are concerned with is sampling from this P, and this P is set up to normalizing constant, up to CT. So, what methods do you know how to sample from a normalized distribution?
Dynamics.
Yeah, right. This is very complex. For today's talk, at least. No, don't look at it. Don't look here. Anyway. Okay. Okay, we will start from basic Monte Carlo, and this is a slide mostly with notations. So we assume we can sample from P. Let for now don't think how we will do so. But for now, let's say if we can sample from this distribution, we can also approximate it, and we can approximate it as a mixture of delta functions. And delta functions in those samples that we have obtained from this Pt. We'll denote this approximation by hat over P. Then, if we have this approximate distribution, we can integrate any function of our choice with respect to it. And basically any integral over this discrete or the mixture of discrete measures will give us just the sum over phi over our function of interest evaluated in the points that we have previously sampled. We will call this, we will denote this by E with some superscript denoting what technique we are using for now. What is cool about the Monte Carlo integration? It's the very last formula. The variance of this estimate, the variance of our E and C, does not depend on the time explicitly, and it has rate 1 over n, and it's very cool. It's very cool because if you will take any any other integration scheme when you say okay, some other method, you will bump into this dependence on t, and this t, I remind you, can be very big. So this is a good fact, and we will build upon it. So the basic Monte Carlo isn't very good, though, because we cannot sample from high-dimensional and complex P. And I have just tricked you. I said we can sample, but in fact we cannot sample
and
from.
That's exactly the place where dependency on T is hiding.
Well, yes, at least yes. And also, when your agent is working in some environment, when your robot is going into some place, and the time goes only forward, you don't want to resample when the t is incremented. And this is important because in any practical application of filtering, you are very concerned with it. You want a fast procedure, fast tracking procedure. And we will going to address each of these problems, at least partly. The first problem we will address with importance sampling, and the second problem with sequential importance sampling. I will introduce each of them in a moment. So,
but why can't we sample from pi, say by chain rule? Why isn't it efficient?
Because it's very high dimensional, and we know it only with respect to some normalizing constant.
Okay.
Okay. So, importance sampling. Importance sampling is basically a very simple procedure. Here it is denoted with 3 consecutive steps. On the first step, you should choose some the so-called proposal distribution Q, and then you can sample from this proposal distribution, and reweight your samples according to the density of Q at this particular point, and the particular unnormalized density you have. We will denote it by gamma. This is a very simple procedure, but you can also this procedure is of very high variance. You can balance, not balance, but yeah, you can lower the variance for the price of some bias. If you renormalize the weight, this version of importance sampling is called self-normalized importance sampling. And then, if you do so if you renormalize the weight, as it is written on the slide, your approximation of P will look like this. This is also a mixture of discrete distributions of delta functions, but each delta function has its own weight W, and this W, capital W, sum up into one. Okay, and what you can do with this, with such measure, with hat P, you can estimate the normalizing constant. This is great. This is great, but this is great because two properties. This way you get the unbiased estimate of your normalizing constant, and this normalizing constant will be of great importance, in the very end of our talk. And also, the relative variance is big O of 1 over n. This is again the good side of importance sampling. But the second problem is unaddressed for now. We still need to resample the full z on the increment of time of t. And to mitigate this, we introduce the sequential importance sampling. The sequential importance sampling is basically importance sampling, and the only difference you should do when you switch from importance sampling to sequential importance sampling is reweighting procedure. So in the importance sampling, the weight you have assigned to your samples were gamma over q, and now when you need to sample one more z of the next time step, that is, you do this at the second step. You need also to change your weight, and what is written on the slide is the very basic and also the very general formula. We will see how it greatly simplifies for the filtering task in a while. So for this, what to do? You should multiply this all estimate. Not all, basically. This is a new estimate. Okay, this is a new estimate. Say you have an estimate for you have W of z1 from 1 to t minus 1, and I want to express W of z from 1 to t in terms of your already computed previous weights. So what you do just multiplying and division by the same quantity by gamma z from 1 to t minus 1, and also some decomposition of your proposal distribution by the chain rule. That's all, and you call this first multiplier as alpha, and here is your previous weight you have computed at the previous step. So great. Now you know how to sample. You know how to mitigate the need for resampling at each increment of t. So what could go wrong? you're right. Explode or vanish. Explode or vanish will term this problem as enormous variance. So, for example, consider maybe the most simple example of sampling from some factorized normal distribution with mean 0 and variance 1. We split this distribution into unnormalized gamma and normalization constant, and also we formulate the proposal as factorized distribution, and this proposal also is also the same of the same factorized family, and the only difference is that we don't know precisely what the variance is. Then, according to the formula of relative variance in estimate of our normalizing constant, we have such interesting expression, and this expression have t at the exponent, and this is extremely bad because for almost perfect proposal distribution, when you have the sigma equal to 1.2, to obtain relative variance of 0.01, and for some not very long sequence for t equal to 1000, we would need 10 to the power of 23 particles samples. This is clearly impractical.
And the reason is, I guess, because the weight of the particle will be just a product of t multipliers.
Yes.
Right?
Yes. And this is because
each particular multiplier can be more or less okay, but the product
yes, but
will tend
the
to
whole
have
product
extremely large variance.
Yes, and this is the very motivation of the sequential Monte Carlo. Sequential Monte Carlo addressed exactly this problem, and this was really the revolution in the control field, in the control area, in the field of tracking some autonomous devices, and still it's very widespread in very different areas such as medicine, such as physics. So to impress you as a sequential Monte Carlo in the same setting with the same proposal, we will require to obtain the same relative variance of estimate of our normalization constant. Will require only 10 thousandths of particles. The 10 thousandths of particles we can simulate on every laptop, any laptop, and this is not a problem, even for your telephone. So the sequential Monte Carlo, what is it? The sequential Monte Carlo, in its generality, is the family of methods for sampling from a sequence of distributions. And this sequence of distributions that we call P with a subscript T is usually indexed with the increasing dimension T. So we assume that this P with index T can change over time. And this change may be very different from time step to time step. What do I mean by this? I mean that PT may not be nested in the sense that the previous PET minus 1 will not be equal to the marginal of PT at the subsequent step. And this is okay for Monte Carlo, for the sequential Monte Carlo. And the same, at each time step, the sequential Monte Carlo provide an approximation PT for the distribution we are interested in for sampling from, and also the estimates of normalization constant.
Could you please tell again what is the difference between PT, well actually pi t and pi t minus 1?
Yeah, this you can think about this as some family of probability distributions which may be unrelated to each other at all. They are just of increasing dimension t.
But the dimension, well, the dimension of arguments is the same, right?
Yes, it's the same.
T minus 1.
It's the same, but the measure you obtain by integrating the subsequent measure p with index t is not equal to the previous measure you have asked to sample for.
So the left-hand part expression is just a result of marginalization with respect to zt.
Yes, yes, exactly. This technique is very simple, but it's very hard to analyze. And in its very simple form, why is it simple? Is it simple because sequential Monte Carlo is nothing but sequential importance sampling plus resampling, and this resampling is the crucial thing here. This resampling changes everything, and I will show you in a while. This sequential Monte Carlo has very strong theoretical guarantees with very mild assumptions, and this is cool for the theoretical guys, but it is also cool for practical guys because it's very practical, and it exists for about 20 years in the form I will tell you about in a moment, and it's really very explored field. There are many results, theoretical, practical. There are many variations, many algorithms that use this sequential Monte Carlo principle. And maybe you have heard about the particle filter. The particle filter, as we will see, is just an instantiation of the sequential Monte Carlo principle for some specific set of distributions that we are asked to sample from. Okay. So let me tell you what is the exact procedure of sequential Monte Carlo. So we start exactly as we have in importance sampling. We start with sampling n particles from the first proposal distribution Q. Then we compute the importance sampling weights and subsequently renormalizing to sum to 1. And then here comes the difference. The difference comes at the subsequent steps, and this difference is in sampling the ancestor indices. By sampling ancestor indices, I mean you at time step t you choose which previous subsequence you want to continue, and this is done by sampling this index from a categorical distribution, from a discrete distribution, with the parameters w, and these w are nothing but your normalized importance sampling weights from the previous time step. This may seem very simple, and it is in fact simple, but the consequences of this resampling step are very profound. So after you have sampled these ancestor indices, you then, exactly as you have previously, sample n particles from your proposal, but now conditioned on the specific previous trajectory, on the specific prefix, which is indexed by the uppercase A. And uppercase A, I remind you, is nothing just an index, just the number from 1 to n. And the third step is again the same we have done at the step 2.
So in some sense, we say that we're taking the set of particles, and then we perform something pretty similar to genetic algorithm. So only the strongest particles survive, and
this is also known as the principle of survival survival of the fittest, of those particles which have the biggest weight. That is the biggest important sampling weight. And we also, I have said to you that that at each time step we can provide an estimate of the normalization constant and also an approximation of the peak. And here is how we can obtain these estimates.
Can we also make analogy with the beam search?
Yeah, I have thought about it, but the beam search is
It's more not in research.
it's not a beam search, right?
It's not a beam search, but there are some similarities.
Yeah, of course. But beam search is looking is doing a look ahead, and this well, there is one variant of the sequential Monte Carlo, which is called the block sampling, in which you, while standing at time step t, you can resample the L previous particles. L, I mean t minus 1, t minus 2, and t minus 3. And this may be seen as some sort of beam search. Maybe not exactly, but sort of. Yes?
This second formula means that the t step of i's particle is a continuation of a trace of a sub t minus 1 particle. So
Yes. What's going on? Let me draw it. What's going on? You have some particles, some purple particles at step t equal to 1. And then you are to sample at the second time step. And what you do for each particle, when you are going to sample the new particle, you choose what the ancestor would be. And this may be maybe like this. This particle has low weight, this is high, and these are zeros. So your second moment will be like this. This particle will choose as its ancestor the first one. This will choose the second one. This will choose the second one. This will choose the second one, and so on until at the very beginning, at the very end, you have you will obtain something like this. This is your sort of ancestor tree, and this may be a problem for these methods. But let me just continue one step further.
May I ask?
Yeah, sure.
Question. Why are you saying that big weight W means that this is a good sample? This weight can be big if we have very bad proposal distribution Q. For example, if unnormalized density gamma is big and density Q is small, then the weight will be big. But it doesn't mean that.
Yeah. What in this case the big weight will mean? If your proposal distribution density at this point is very low, it means you're very unlikely to sample in this region.
Okay.
But in this region, your gamma, your unnormalized density, is very high. So, in fact, because this unnormalized density is high, you want to sample from this region.
Okay.
But your density is very low, and the chance you will sample nearby this area the second time is very low. So you can you should multiply the number of such samples. You should sample more often in these areas. Okay. So this is a tricky part. This is a tricky part because this is a comparison of comparison of relative variances. Variances in estimates of the normalizing constant. And the first guy is the one we have already seen, and this is for the sequential importance sampling. And the second guy is for sequential Monte Carlo. And these expressions may give you some intuition about what's going on. Why does the sequential Monte Carlo works good in practice? So, what can you see here? In the first expression, at the denominator, you have one Q, and this Q is a density over the product of T spaces, right? Because you in the denominator you have the density of your whole hidden history, not hidden, sorry, all your history from 1 to T. And what's going on is in sequential Monte Carlo when you do a resampling step. Let me just ask you, why this step may be called resampling? Why not sampling? Let me go back. Why do we resample?
Because you sample again.
You sample among samples.
Yes, you sample among samples. Okay.
But you sample new samples, but from samples.
Yes, we should stop somewhere in this sample. So, what you see here, what is interesting, is this sum. This sum means you have broken this integral over all your space into a set of smaller integrals. And these smaller integrals also have your density, your target density at the denominator. This also, so even if your proposal is bad, it may be the case that you have sampled in the area that your target density, in which your target density is high. And in this case, the denominator will not be small, but will be moderate. And you will not have the inflated variance of your normalizing constant estimation. Okay.
Why is it an approximation?
Yes, this is an approximation. This I have challenged myself to track it down, but I have failed to do so. About 20 papers I have seen, they all say that there was some clever guy in 2004, and he wrote a book which is 500 pages long, and this is a book about Feynman-Kak formula. Do you know somebody? Okay. For those of you who shamelessly don't know what is a Feynman-Kak formula, it is a formula that connects the parabolic or paraboloid, I'm not quite sure, parabolic partial differential equations and stochastic processes. And this is a book which I can't read, but all the theory about the sequential Monte Carlo is there. So in case you are interested in, you can just skim through it.
But like the theory says that it's approximation.
Yes.
And is there a guarantee how good the approximation is?
Yes. If you're asking about is there some theoretical formula or theoretical result about something about sequential Monte Carlo, the answer is always yes. So,
but can you parse this result? Can you parse this result? Is it good?
Mostly no. I will show you some of the results I can parse, but in a few slides forward. Okay. So, yeah.
Parabolic differential equation, you mean
Partial differential equations.
You mean focal point equation?
I'm not sure. Sorry. Okay. So the bad thing about the sequential Monte Carlo is the reality we are all facing. You cannot. It's in theory as well as in practice. It's impossible to accurately represent a distribution on a space of arbitrarily high dimension with a sample of fixed finite size. So you cannot just have some small number of particles and approximate the very high dimensional distribution. This is just not possible. And this is the problem everyone in this field face, and this is exactly the problem that is related to this ancestor tree. At each time step, let me remind you, at each time step you sample an index from an index which may be from 1 to n. You can just lower the number of previous histories you are considering at the next step. You cannot make it more diverse, and this is a very serious problem. And there are many different solutions. Some of them are here. The very first thing you should do to mitigate this, I'm careful about my words, not to solve but mitigate, and also to some extent, is the controlled resampling. Controlled resampling is the controlling of the variance of your weight. So if at some point you have realized that all of your weights are 0 except 1, you have probably the very degenerate particle set, and all you will do in the future will be mostly pointless. So the second thing you can do is you can do some sort of advanced resampling. The advanced resampling means you don't sample according to just multinomial distribution. This the first step, but you make some fancy different scheme which is also sampling, but this sampling was developed exactly for the purpose of lowering the variance of your weight. The third thing you can do is the block sampling and auxiliary particle filter, and all these and many other ideas fall into the bin which is called look aheads. You can look ahead of what you have, what observations you have in the near future, say at some near lag of some 1, 2, 3, or 10 future observations, if you can. And according to these distributions, adjust your sampling at the moment which you are staying, which you stayed 10 time steps in the past. So if it's not clear, it's okay, because I'm not going to tell this into detail. And the last thing I would like to bring to your attention is the resample move technique. This is very interesting technique, which is for my okay. This is a technique which may be used with neural networks, and maybe this will be some prominent future research direction. So this technique is about marrying your sequential Monte Carlo and your some sort of Markov chain Monte Carlo, or Markov chain Monte Carlo. Okay, sequential Monte Carlo and Markov chain Monte Carlo. In the very essence, these two techniques are good at the very different things. The sequential Monte Carlo is good at finding the modus of your multimodal distribution. And the Markov chain Monte Carlo is good at sampling inside each of the modes. So if you happens to know how to combine them and actually marry them, this will be very great. So for the state of the art for now is this the Gibbs sampling, the PGAS algorithm, in case you are just interested in. So let me go back to the filtering, because this is the thing we are actually interested in. And let me remind you that the problem we are started from was exactly the posterior distribution was the PZ conditioned on your observations up to moment t. So these two formulas you have already seen, and what are we going to do now? Now we do not what we have developed. We have developed a method to sample from this posterior distribution. Let me ask you, what is the gamma here in this filtering context? What is the gamma? Gamma of Z1T.
Probably the numerator.
Yes, the numerator.
Oh, it's it.
I'm just asking, not you, Peter.
Okay, sorry for that.
Sorry? Okay, so now we know how to sample, and these samples are not the waste of your time. This is great, and I will tell you in a moment why they are not so. In fact, what you have now, you have some approximation of distribution, and this you approximate these distributions with the mixture of delta distributions, and this mixture is a very convenient form to work with. You can marginalize over all previous z from 1 to t minus 2 and obtain the filtering distribution at time step t minus 1. And this you can do without even bothering yourself about what is your dynamics. You don't need to think if it is Gaussian or it's, I don't know, log normal or anything else. You just sample, and you just sample from your forward dynamics. This is great. This is really great. Then when you have obtained this filtering distribution, you can resample. That is a sample from this filtering distribution according to the weights, according to your normalized importance weights. And after this sampling, pay attention here, because this sampling is exactly the same as the sampling the ancestor indices. Okay, and so you're obtaining again n samples, which are for now are equally weighted. So we don't have the w's in front of after the sum. We have 1 over n in front of it.
But we have the same zi's minus 1.
Yes, yes, we have the same set.
We can have
the reduced set. Okay, and here comes the interesting part, which will be of great use in variation sequential Monte Carlo. We are also interested in the denominator of the Bayesian formula, the Bayes formula. Here it is written on the left. And what we are going to approximate it with, we are going to approximate it with we are going to take this integral over the z t minus 1 till t. And we are going to do so in 2 steps. In the first step, we are going to just integrate it with respect to this p with bar. And this p with bar, I remind you, is just the mixture of delta distributions. And if you integrate the mixture of delta distributions, you just arrive at the sum over the arguments of the delta functions. And the second step, what we are going to do is we are going to sample from the proposal distribution here at the Q, and this is why we just divide it and multiply it by this Q. And by sampling ZT with index I, we are obtaining an estimate of the conditional density.
Why couldn't we simply sample from F?
Yes, we can. If we know how to sample from F, and also know G, this is also possible. Okay. Now we are going to slightly increase the level of difficulty. We can model our dynamics, our F, G, and our proposal as some complex distributions which depend not only on the previous Z, but also on maybe also on the previous history, on the full previous history. This adds a lot of flexibility to our model, and this still allows us to estimate the marginal likelihood and do this unbiasedly. So how do we do so? This inner sum with multiplier 1 over n is nothing but the approximation of the conditional distribution. And when you take the product from t from 1 to capital T, you just get an approximation for your marginal distribution. And the marginal distribution is the very useful object which we will heavily use in a while. So let me talk about, a little bit about theoretical results, which I have managed to digest from the literature. So the main assumption which is made, but it's not the only way to talk about theoretical results. I mean, through the lens of this assumption, we can make less strong assumptions. But for this one, which is all about the forgetting principle, that is, at time t, if you observing all the history, all the x from t from second step up until now, this is you're almost indifferent about what exactly was the first hidden state, and you are saying by this assumption that this difference in distributions for any z1 and z1 prime, which are two different initial latent states, decrease exponentially with the time horizon.
So in some sense, we say that there are no long-term dependencies.
Yes, there are no long-term dependencies. In this case, everything works great, and you can say that your estimate of your posterior distribution, your expectation of it, of your estimate, its absolute variance from the true posterior distribution is bounded with the time horizon, with t, and the t is included in the right hand side in the first linearly. I mean linearly, and this is great because if you set the n as some quantity which is proportional to the time. You say that n equal to some constant times t. This allows you to control what is the discrepancy between your estimate of your posterior distribution. This is great. You can also say many interesting things about your marginal distribution, about the p hat of x, of x, and how it relates to the true marginal density. And this is a central limit theorem. Again, this may seem that these three words may be very familiar to you, and you may think that this is very easy to derive, but please believe me, it's not. And also the third result I would want to talk about is the relative variance. That is the relative variance of your estimate. The square of it is also bounded linearly with the time horizon. And again, this is a great thing. This is a very great thing. Okay.
Where is there alpha any day in these results?
No, the alpha is only at your assumption. This alpha should be. This is basically your assumption of how fast you forget the very distant past. And that's all.
So basically,
if you're asking if this B1, B2, and B3 depend on it, well, yeah.
Are there explicit dependencies?
As far as I remember, yes. But I may be not quite. I'm not quite sure about it. Okay. So we have talked about how to improve your resampling process. But you can also work with your proposal. You can improve it, and you can improve it in many different ways. I have written just few of them. You can estimate what is the mode of a true posterior at the next time step. You can do some local approximations. You can do some local linearization of the complex system dynamics, if you can, of course. Yeah, and this lead to the family of different algorithms which heavily based on the Kalman filter. And you also can do something that is maybe more interesting, the implicit proposals. But what we really care to improve upon the fixed proposal. We care for the parameters of Q of our proposal and about tuning these parameters according to the particular task at hand. And can we do this? The answer is yes, and the answer is the variational sequential Monte Carlo. This is a very interesting technique because it melts two different, very strong and very practical family of methods. One of them being the sequential Monte Carlo methods, and the other one is the variational methods, which maybe all of you are already aware of. So in the very short gist of the algorithm, what you do, you parameterize your proposal distribution. The proposal you are using in the sequential Monte Carlo algorithm, and you optimize the Cal divergence between your proposal and the true posterior. And this optimization is a very interesting one because you can, in fact, bound the discrepancy between them, and I will show it in a minute. Okay, and then to sample from your new variational posterior, from your Q, you just run the sequential Monte Carlo and pick one of the particles at the very end of it. This is great. This is great not only because you melt together two very strong practical algorithms, but it's also very cool because you can apply this algorithm to any sequence of probabilistic models. The model does not need to be sequential. I have shown you the sequential application because it's probably the most intuitive one, but you really don't need to. because the sequential Monte Carlo algorithm can be applied to non-sequential algorithms too. And in essence, the variational sequential Monte Carlo allows for model learning, for proposal adaptation, and for inference amortization. Exactly in the same, exactly all the same that you have probably done before with some variational autoencoders or anything like this.
Do you assume here that we actually can't sample from F?
Can't sample from
Can't.
Can't.
Or we actually can, and this procedure is able to do better proposals.
In fact, what you need in this algorithm, you need to compute where have this slide? You need to compute this weight, and you may be not allowed to sample from F, but you are allowed to evaluate its density at the points which are the samples from your proposal distribution. Or otherwise, you may be allowed to sample from F, but not to evaluate its density.
But if we are allowed to sample from F, the reason of using variational schemes.
What's the reason for using variational schemes?
Yeah. Why not just take these Z's with the weights equal to 1? Or the weights proportional to G.
To G.
Yeah. So I would assume that the only reason of establishing variational distribution Q is the fact that we can't sample from F. I'm
Okay,
not 100% sure.
I guess you're right. I guess you're right. But if you can sample, you can just avoid using any variational sequential Monte Carlo and just do 1 over n sum of G of your samples. Okay.
So any switching to Q actually makes our model worse. So the only reason why we need to do it because we can't sample from F.
Yes.
And then there's a dependence of how good is Q. So the better is Q, the better is our model. This is why variational scheme arises.
Wait, but are you sure that the optimal Q is F? I don't think so.
The optimal Q is a posterior distribution. The posterior distribution over that subscript T.
So this is probably proportional to the product of F times G.
Yes. That's
Yes.
the case in the typical important sampling.
Yes.
Okay, so it may be better to sample from Q rather than from sample from F and perform the weighting.
Yes.
This is the reason.
Yes.
Yeah.
Yes.
So and we assume that we can't sample from the product of F times G,
But
and this is usually the case.
sampling from product of F and G is just sampling from a normalized posterior.
Yeah. This is not trivial in general case, because we need to warm up Markov chain.
Yes, but we may be interested in obtaining this posterior in some closed form, parameterized maybe based on a neural network or something like this.
Well,
And this may be the second case.
This is the second use case.
Okay. Yes. So now let me remind you what is ELBA, and I will remind you in slightly not usual way. So you can pick any normalized target density. That is the gamma in our talk. It's denoted by gamma. With normalizing constant capital C, again as in previous slides. And use some proportional density Q, which should be the capital Q. Sorry. In this case, the alpha, which is the lower bound of logarithm of the normalizing constant C, we can denote it like this. This is an expectation of the logarithm of a normalized density over our proposal density Q. So this is very maybe very familiar to you, but let me step one step further. Let's assume that the C with the hat is non-negative and this C with a hat is an unbiased estimate of your C, of your normalizing constant. And by unbiased, I mean that the integral over your proposal density, over your Q, is equal to your true normalizing constant C. What we can do in this way, in this case, we can plug this gamma, this unnormalized density, which is now QZ times C hat, into this expression, and for any unbiased non-negative estimate of your normalizing function, you will get new alpha. This is yes.
Why gamma equals to the product of Q times C hat?
I can't say why, because this isn't what, there is no why. You just say that this QZ times C with a hat, you can view this product as some unnormalized density from which you want to sample. Sample or do anything what you are just want to do. This is just, yeah, we can say that this product, we can call it gamma.
Okay, but before your gamma was just a normalized version of pi. So now gamma is something different.
Well, not exactly, because this may be the gamma for some another pi, a normalized density. So this is just gamma. It just stands in this talk. Gamma just stands for some normalized density, and
no, Pasha, you seem to miss something.
okay.
Because there are too many requirements. So we know that there is gamma distribution whose normalizing constant is C, right? We know that there is some function C hat of Z, which is unbiased estimate for C. I can't see why the product of Q times C hat equals to exactly this gamma distribution.
It's in the very beginning. There is written for any unnormalized target density. So I can choose any unnormalized target density.
Yes, but C hat is related directly to this normalizing constant C.
Can we just define C hat as is gamma divided by Q?
Yes, we can, but then we need to prove that C hat is unbiased estimate. You see? Because there are too many restrictions. One should be consequence of other assumptions.
Let me again.
But it's not that hard to prove what you said.
Yes.
I mean, C is by definition the integral of gamma.
Yes.
Then you just put the definition for the C hat into the integral,
Yes.
into the integral over Q. The Q's go away, and the only thing we have left is C equals to integral of gamma.
Yeah.
So what about lower bound? For which value this alpha is lower bound?
For which value of what? Of gamma?
Of some expression
Okay.
for which this alpha is lower bound.
Let me start this way. Do you have any questions with this?
So you see that this alpha is
So
lower
you
bound
define
for log
C hat
C.
first.
Yes.
Okay.
And the same question for the next alpha.
The next
Because you can see
isn't an
different
alpha.
unbiased
exactly.
estimates.
This is a unifying
But this is
principle.
specific unbiased
This is a
estimate.
unifying
C hat.
principle which tells you that if you have the non-negative and unbiased estimate of your normalizing constant with some pretty much any structure, you can plug this this estimate into this formula and obtain a new alpha. This is
Pasha.
yeah.
C hat is already defined. This is not arbitrary unbiased estimate.
C hat.
C hat is by definition a relation of gamma over Q.
C hat is not. C hat is an estimate. Here we have only C, and we have the quantifier any.
Yes, but C hat of Z
C hat of
is
Z.
by definition a relation of gamma of Z over Q of Z. This is not an arbitrary unbiased estimate for normalizing constant. This is quite specific unbiased estimate. Only then we can proceed.
C hat. Can you?
Yes, this expression contains the definition of C hat. So C hat is simply gamma over Q. And only this C hat.
Okay.
For this C hat, you may write down the following expression. And this C hat is a really unbiased estimate, and this integral equals to C.
Yes.
But we may mention some different unbiased estimates here, but these are not C hats. Because if we substitute here some arbitrary unbiased estimate, this equation probably will not hold true.
I think
So
we should move further where we are using this formula, because now it's just
Okay,
inequality.
let me show 2 examples. I guess they will.
What's the difference between capital Q and...
It's the same, I think.
Sorry, I just messed up. This Q should be the capital Q everywhere. This slide. Sorry.
Why did you say that it is a different elbow? Why not?
It's the same elbow.
It's the same.
It's a different equation.
Yes, it's a different form. So you have probably already familiar with elbow in the variational autoencoders and the form of elbow which is used in eBay. And in fact, just ask me. I will help.
I'm not sure I understand what I want to ask.
So
Why this C hat does not depend on it?
This is more or less for the
For
sure.
fixed X?
Yes, fixed X. I guess so.
So, okay, from what is written here, we have different gammas, but with different gammas, all different gammas still have the same normalizing constant. Agree?
Yes.
Then this is
Yes.
fair.
Yes. Exactly.
Okay.
Okay. Any
How
questions
can,
here?
how can different gammas have same normalizing constants?
Oh, we can
Why not?
It's
imagine.
like very specific family gammas.
Yeah.
Okay.
Please.
But for these 2 examples, this is the case.
What I will say what I'm going to do next. I'm going to define a new C hat, and this C hat will be somehow related to sequential Monte Carlo. And this is the way to obtain a new alpha which relies upon the sequential Monte Carlo. So if you don't understand this, you will not understand the variation of sequential Monte Carlo. So please, maybe I have messed up something here. So just ask and I'll try to.
And what is capital Q for this example? For I and I where?
For this example, the capital Q is just QZ over X. You can just plug this this fraction into this expression, and recall what is the elbow for the variational technique.
Okay, and for this case, yep. What is capital Q? Because here we have k different distributions, right? K
Yeah,
different
this-
Q smalls.
For this one, we have the capital Q will be distribution over the 1 over k different depth. It's for the vector, each component of
Oh,
So here is that
this
K.
is subscript, yep. So Q of the k given X. It should be, right? In the denominator.
This subscript of k should
Yeah,
not.
sorry.
So now uppercase Q is k-dimensional distribution over Z.
Yes. And now on the next slide, I will define the capital Q and the C hat for the sequential Monte Carlo.
And why the normalization constant is the same? Because this is normalization constant for P of Z given X
P of Z
in both cases. Ah, yeah. Probably
Yes.
this is it.
Yes.
So this could be an answer to your question, Anton.
So, this should be a little bit scary, but in fact, everything that is written on the slide here you have already seen. So, what is the capital Q for the sequential Monte Carlo? In fact, it is a distribution, joint distribution over all random variables that you generate in the sequential Monte Carlo procedure. You propose Z and you resample. You sample from a discrete distribution A, from discrete distribution parameterized by the importance weighted weights. And this is Q. And we also know what that we can obtain an unbiased estimator of the marginal likelihood, and this is the C with a hat, which was previously defined as the product over time steps and the mean of the importance weighted weights. For the definition of W with subscript T is here, and this is just the dynamics and the observation probability divided by the proposal density. So with this capital Q and the estimate of the normalization constant, we can form and optimize a new alpha. And this alpha would look like this. So this is just the expectation over the sampling distribution of sequential Monte Carlo of logarithm of the unbiased estimate of the normalization constant. And this is interesting because this is a...
And this is our bound to the logarithm of normalization constant.
Yes.
To the Jensen's equality.
Yes.
How do you optimize it? Because you have a categorical distribution that depends on Z
Yes.
and phi.
Yes. Yes, this is the question. What,
Universal answer.
how do you think that is done in practice?
I would say by double stochastic relation inference.
No.
No?
No, we just ignore it. We just ignore any sampling from the categorical distribution. Yeah. Yeah. So we want to optimize it with respect to our parameters. With respect to parameters theta and phi, the theta is parameters of the dynamics of your F and G, and the phi is the parameter of your proposal. So everything we'll do, we make the proposal reconfigurable and totally ignore the gradient with respect to categorical sampling.
And what will be the consequence?
This introduces some bias, but in practice, authors of 3 papers published almost in the same time, one from Oxford, one from DeepMind, and one from the Blay Lab. All of them independently say that this is negligible compared to the variance introduced when trying to account for gradient with respect to categorical sampling.
So they have suggested to ignore the gradients independently in these 3 papers?
Yes. Yes, and I will show the plot in a minute, in a minute, which will...
Interesting.
Yeah, each of these papers discuss this fact, and each of these papers arrive at the same conclusion independently. So the theoretical benefits are as follows. We now know how to bound our discrepancy between the true variational the true posterior and our variational approximation. And the interesting thing here is that this discrepancy measured with scale divergence may be bound with 1 over n rate. So we can scale n as much as we can to reduce this scale divergence. And this is interesting because we can bound the KL divergence in N. But what about the T in this case? In this case, what we can say? We can say that the KL divergence between our variational posterior and the two posterior is less than equal than the logarithm of relative of the fraction of our estimate and the true marginal distribution. And this with t growing to infinity is also bounded by some finite quantity, which we can control with again with how many particles we can simulate from our proposal. And this is also interesting. The bad news are that in general we cannot achieve the marginal likelihood on optimal proposal Q star. That is, we cannot do so in general for any dependence between the latent variables. So the authors show only that if some independence assumptions hold. In this case, they have shown that if the distribution over t-1 latent states does not depend on the
on the teeth point.
Yes, does not depend on the very last observation. In this case, this is fulfilled.
But doesn't it seem strange?
Yes.
Probably this is very unnatural.
Yes, yes, it is. But in practice, they observe very great results. No, this is natural in fact, because you cannot sample from the distribution that depend on your future observations.
And so what? Well, these future observations contain some information about our latent variable z.
Yes.
Anyway.
This is not true even for hidden Markov model.
Yes.
This is right. But this is all they can theoretically guarantee.
Probably if we delete just all horizontal ties,
yes,
switch to independent model.
You can do so because the SMC is applicable to such models.
I understand. But this is not the case as SMC was invited. So for all practical applications, there is a clear dependency between xt and the previous latent variables.
And the others say that they have tried to introduce a backward recurrent neural network that aggregate all the future observations to the moment from the capital T to the moment t, and they observe negligible improvements.
Жуки.
Well, maybe. Well, maybe, but the results are very impressive. If you know, Timit is a data set for the voice modeling, and this is an ALBA. This is an ALBA on the test set, and they outperform really great the usual ALBA, the ALBA for EVA. And they say that the interesting thing is that
What is FIVO?
FIVA is filtering.
This
Variational objective.
The variational objective, right? But what's filtering?
First in.
No, it's filtering.
can be filtering, but too.
Filter inference. Filter inference.
Sorry, I don't know what's E. I don't remember it. They have
This is their model.
Yes, this is a model. This is a model. This model I have called Variational Sequential Monte Carlo because 3 papers obviously have different titles, and this is one of them.
Now, can you say a couple of words about the particular model? Why can't we sample from F in that model, etc.?
why we can sample from F.
And all these methods, are those for different models or for different methods of learning?
No, only on the different methods of learning.
So model is the same?
Yes, the model is the same. But why we can sample from F? Well, one answer may be that we don't know what the F is.
What was the model? Timid data set, what is this?
This is a collection of the voice data sets.
Okay, so there was probably some kind of recurrent neural network.
Yes, there was a variational recurrent neural network. That is a recurrent neural network with latent stochastic variables, and each distribution of each latent stochastic variable was dependent on its parameters were dependent on the full previous history.
Okay, and what was the structure of this queue?
The structure of this queue was also the recurrent neural network.
So recurrent neural network tries to approximate the posterior from recurrent neural network.
From posterior from recurrent neural network.
No, that's okay, just like we do in variational encoder.
Yes.
And how come more samples, n is samples, number of samples inside? Yes?
Yes.
Why, some methods, when you sample more, you get worse performance? Like what method called elbow, for example. Like it doesn't go up.
But I would assume that the number of samples for elbow just reduces its variance, but it doesn't improve elbow.
But
Unlike
why
that
it goes down?
Oh, it's just some fluctuations.
Then, if those are fluctuations, then like, what
No,
does numbers mean?
There is also some subtle fact which may be familiar to you from the paper that tighter bounds are not necessarily better.
Right.
Right.
But
But it doesn't relate to elbow.
Yes, but it's related to eVia.
Yeah.
Because when you increase number of samples in eVia, you make your elbow tighter. Basically, I don't know how to answer about that. I don't.
Oh, but what role is played by the samples in the elbow? They just reduce the variance. They do not increase the mean of elbow estimate.
So
Yes, but then it should be the same.
Well, that's more or
Because
less
like
the
we
same.
get, well.
What do you mean?
No.
Here it's the same. Here it's the same. No.
But in the first column,
The first column, yes, it's not the same.
I mean, where are their confidence bounds?
Yeah.
Oh,
Because-
let me just go further.
I mean,
Okay.
hey, this was a DeepMind paper.
Yes, this was.
They can't
They
complain on
sure
lack
can
of
afford
resources.
that.
But have you seen any paper with reporting alpha on the test set with confidence bound?
I wish.
I wish.
Maybe that's the issue with the elbow.
Even our papers, which are under construction, does not do so. What can we say about DeepMind?
Your cluster is much bigger, yes.
Okay, let me proceed. This was a comparison between the model which accounts for resampling, which accounts for categorical sampling, and which does not. The higher results, as you may imagine, is for the model which ignores this gradient with respect to discrete sample, and this is a consistent fact in all three papers. And this plot also shows that the KL divergence between the prior, between variational posterior and the prior. So this is an illustration on the problem of ignoring the stochastic variables. So when you add stochastic variables to your recurrent neural network, it may altogether ignore all your stochasticity and act only according to its deterministic transitions. This is, I believe, more or less a standard way to show that the model really accounts for your stochasticity and use it. So we see that the variational sequential Monte Carlo has the biggest scale divergence between the variational posterior and the prior. So we may hope that it make use of the stochastic variables more.
Wait a minute. This is scale divergence between variational approximation and prior or posterior?
And prior.
But then why it goes down for elbow? Because elbow optimizes directly scale divergence between variational approximation and posterior.
Yes, but not the variational posterior, but not the co-divergence between variational posterior and the prior.
Right. And why it's minimized for elbow?
Probably it means that the model learns to ignore the latent code.
Yes, yes. This is exactly what I could just say. They are not the first paper where I see this the results of such kind. So I believe this is a more or less standard way to measure dependence on the stochastic variables. Okay. If you have fallen asleep, please wake up because the talk is over.
The most important slide.
Yeah, this is the last slide. If you're interested in some hardcore theory, please drop me a line. I will tell you in what books you can find them. But I really don't recommend this. I have tried for half of day and I have gained nothing. So maybe you.
From the books?
Yes. From the one book. This is a book about I don't know how to parse it. So if you have any experience with parabolic partial differential equations, please come to my table.
But have you found the papers, these three papers, useful? Including one from DeepMind?
Yes, but many of them does not cite. For example, let me go back and let me ask, why have you agreed that this estimate is unbiased? This is not obvious because what I have shown you, only what I have managed to do. I have shown you this that you can believe that this one is the unbiased estimate of this quantity because you can just make expectation with respect to Q and you've just done.
Mm-hmm.
But this is not the truth for the product because if you have an expectation of the product of unbiased estimates, doesn't mean that the product of unbiased estimates is unbiased. This is.
Well, it depends on whether they are independent or not.
Yes, but they are dependent because the whole sequence is dependent, and this is notoriously hard thing to prove. I have failed, and I have failed to find anyone who points to the source. All these three papers, 2 of 3 papers doesn't anything for this unbiasedness, and only one of them from the Bly lab, if I don't mistake, cite this paper, this book of.
So probably this is universal solution.
Yeah,
if you always cite such kind of book which is unreadable, nobody will understand that this was a fake site.
Well, that would really depend who you get as the reviewers. When I'm a review, if I get like this, well, I will get so annoyed.
So I believe the way to prove this is to somehow go back from the sequential Monte Carlo to the full sequence and derive something from the full sequence, just like we derived in the important sampling case, the unbiasedness. But it's directly I haven't done this. I have tried and I haven't catch by the top. Sorry.
Any questions? Well, there are no questions. I have just a couple of concluding remarks. So although this technique may seem to be, well, quite difficult, but this is interesting and promising because such kind of mathematical tools allow us to generalize well-studied state space models for the case when We can use recurrent neural networks, or just standard neural networks for emission probabilities and for transition probabilities. So this is important. This is one of the trends in machine learning, when we try to take classical models for data processing, and we simply remove some linear dependencies, some simple distributions with the deep neural networks. And so the inference algorithms change, and this is the example of how standard inference for state-space models can be modified in order us to be able to work with deep neural networks. So that's quite interesting, promising, and hopefully effective. So not surprising that such kind of research is performed by Bayes Lab and by DeepMind. So let us thank the speaker for very interesting and insightful talk.